Early windmills were a familiar sight in Europe, and smaller adaptations dotted the American landscape at the turn of the 20th century and beyond. With the westward expansion, millions of windmills were erected to pump water from farms, ranches, and the railroads. They were perfect for the isolated reaches of North America. In 1860, Moses Farmer, an electrical engineer and inventor from New England, experimented with converting wind energy into electricity. In 1888, Charles Brush was the first to use the natural power to create electricity for 350 incandescent lights, 2 arc lights, and a number of electric motors. But it was in Europe where thinking about wind power to generate electricity began in earnest. In 1906, Paul Lacour, a Dane, built 40 windmills to generate electricity in Denmark. In subsequent years, wind power was also used to generate electricity in Germany and Great Britain. But it was not until much later that they were used to promote renewable energy. In 1978, the US government required regulated power utilities to purchase electricity from qualified generating facilities that used alternative energy sources. There was a 10% federal tax credit on new investment in capital-intensive wind and solar generation technologies. The state of California adopted a similar mandate. The Danes went even further, requiring utility companies to accept energy from wind. Fueled by the US federal wind power program, first-generation prototypes were built, incorporating technology developed by the aviation and aerospace industry. In the early days, Danish companies built 90% of the new installations in California. Unfortunately, many of these early projects were plagued by technical failures, and it became obvious that engineers needed to learn more about both the technology and the operating environment. Although most of the world's wind turbines were located in the United States up through the mid-1980s, it was an uphill battle to gain acceptance for wind energy as a major energy source. Wind energy was thought to be too unpredictable and too costly, and in 1985, the US discontinued incentives for wind energy. Leadership to develop wind energy shifted to Europe, where the public policy environment was more favorable. As a result, European countries stepped up their wind energy program, which led to the growth of an industry.
But I think the excitement about energy in the early 80s gave rise to a tremendous interest from both Europe and around the world, but Europe, Northern Europe, particularly Denmark and the US, were competing with technical solutions, that is, different technical designs. In the US, you'd see two-bladed machines and very small machines by today's standards, but large by those standards. And Denmark had a very different design approach, a three-bladed rigid rotor kind of approach, and very heavy. Those two competing designs went through the mid-80s, and frankly both had quite a lot of problems. So when I say if we had been called to duty in the early 80s, we really would not have been up to the task. Those machines were functional, but the reliability was pretty bad.
Toward the end of the 20th century, engineers advanced breakthrough technologies to harness wind power and set the stage for it to become a major player in today's alternative energy picture. Steady technology innovations in the United States and Europe laid the foundation for today's growing wind power industry.
We really didn't know our most fundamental design problem, which is predicting the environment within which these machines had to perform. And the wind turbine problem, design problem, is a tough one. It's we have to live or design machines that'll last for 20 years, and in a single year, a wind turbine will put on 6,000 hours of operation. And for the automotive equivalent of, it would be 300,000 miles on your car without having any maintenance. We needed to know the loads very accurately, and they're all fatigue loads, they're dynamic loads. So our testing really led to much better understanding of what the loads were coming from and how we could model them. And in the 90s, we set ourselves to developing much better aeroelastic dynamic codes. And those codes have been used to propel the new industry.
These large windmills, so you're putting a 200-ton thing on a tower, and that 200-ton thing has to turn, rotate. not only the blades rotate to get the wind, the whole blade axis has to rotate to face the wind.
The materials used in wind turbines are as good as they need to be. That's the best description I have. The materials used are really, really exotic in places like gear teeth and in bearing technology and synthetic oils that are used in the gearboxes. Very expensive, but designed to have a very good fatigue life, but be as light as possible and as inexpensive as possible. In places like the tower or in the nacelle covering, it's very low-tech material. The tower is made out of very low-grade steel, but adequate for the job because it doesn't need to do anything except resist the overturning moment of the machine. The concrete for the foundation is nothing special, 2,500 or 3,000 psi concrete with traditional rebar installed, so nothing special there either. All the cabling and the transformers and so on are things that have been used in the electrical industry for years and years. In the blades are made out of fiberglass, and you may think that as being an exotic material, but fiberglass has been around for 60 years or more in commercial applications, used in sporting goods and in cars, the Corvette for instance, and many other applications for many, many years. And the reasons that it is used is because it's a very inexpensive composite, and composites as a general rule of thumb are very resistant to fatigue. That is much better than steel or aluminum and so on, and the fatigue life that a blade has to endure is much worse than anybody can possibly imagine. Steel wears out very, very quickly in a matter of a year or so. Aluminum wears out in similar time frames, so you don't want those kinds of fatigue failures occurring in blades that are spinning around at 12 or 15 RPM with tip speeds in the 200+ mile/hour range. You want to make sure that they're going to last 20 or 25 years. Composites in the blades are the way that's done.
It appears that no matter where wind turbines are sited, along the coast or out to sea, one of the greatest challenges they must meet is coping with the effects of their power source, the wind, which at times could become quite violent. All utility-grade wind turbines are certified to international standards that specify turbine performance under high-speed winds ranging from Hurricane Class 1 through 4. It is the developer's responsibility to make sure that the turbine and foundation they have chosen does in fact take into account 50 years of extreme wind conditions at the site. A local operator explains how these international standards are applied in Atlantic City, New Jersey.
These have to be built to withstand the most extreme weather conditions. Around here, what the concern would be is extremely high winds under hurricane conditions or a northeaster. These have been designed and installed to handle a Category 3 hurricane. When the winds exceed 40 miles an hour gust, the blade is disengaged from the turbine. So it's running free, but then it turns and faces into the wind as opposed to flat against the wind. So there's less resistance. That takes a motor to do that. And of course, in hurricane conditions, that motor would be supplied by the grid. Most likely the grid's out under those conditions, so there's been emergency generators installed at each one of these so that that motor can face the blades into the wind.
All energy construction projects have social and environmental impacts. This is also true for the construction of wind farms.